Okay, just so even though we had the very terrible puns that all the people on the video aren't going to be able to see, I'm going to start off with a little turtle joke. What do you get when you cross a turtle with a giraffe? You get a turtleneck. Okay, just to loosen y'all up a little bit. Okay, so today on Turtle Talk, we're going to be talking about great transitions from ancestral reptilian tetrapods to turtles, the wonderful turtles we know today that look like this. Cute, small, oh, maybe not all of them are small, but cute, kind of got this general idea. There's a little bit of diversity amongst them, but we're going to be talking about why turtles look like this, why the shell developed, what caused the shell to develop, and a lot of differences between common, today's turtles that are now living right now. So this is kind of, everybody's got the kind of general idea of what a turtle looks like.
Okay, and so the origins. Just to bring you up to speed, today there are three main hypotheses of where the turtle actually came from. Yes, in our beautiful little illustration. All right, and so how did the turtle get its shell? These hypotheses developed independently. However, we can find them all together discussed in one of our primary literature articles, Lawson et al. Okay, and just to give you some terminology before we get into this, we wanted to establish what we meant by clade. So since we've all been in the 151 class, we'll be describing clades as a monophyletic clade, so the common ancestor and all of the derived species from there. All right, and so we have three hypotheses. Our first hypothesis is molecular based, so on our DNA, homology of the genes in the genome, and this evidence would suggest that the ancient turtles actually speciated from the crocodile bird clade. However, we have a second hypothesis that is more morphological based, and that's based off our fossil and bone structure evidence, and it suggests that these ancient turtle forms actually speciated from the lizard tuatara clade. And then our third hypothesis is kind of a mixture of both. It is more morphological based because it's more on the diapsid. And so a diapsid means that you have a small opening behind the eye socket of the animal. And turtles had these in their early speciation events. However, they've evolved today to not have these. So that's a third hypothesis that scientists are interested in. And so, yeah.
So like we mentioned, the reason that there's so much discrepancy and there's three different hypotheses is the difference in bone structure. So first we'll look at the skulls. So as you see here, this is a sea turtle skull, and this is the skull of a horny-toed lizard. And as you can see, the diapsid holes behind the eyes have closed up both here and here. But in the crocodile, it's actually an alligator. But anyway, you see the hole right here, directly behind the eye socket. Also, some of the biggest differences are in the rest of the skeletal structure. So as you know, or you should know, all turtles have a shell, which is not seen in any other reptilian species. But they also have their scalculus, which is basically our shoulder blades, but they are underneath their body. So they're inside the shell, which is very different when compared to both lizards and alligators. There's also confusion and discrepancy because of the breast ventral plate, which was formed by the fusion of gastralia, which are basically just ventral or belly ribs, which you can see in many crocodilian species, like right here, where a ventral bony plate has formed through the same mechanism.
All right, so now that we know why this is such a highly debatable topic amongst scientists today, why would a turtle evolve to have a shell? What are the benefits of having a shell? And so this lady named Sue, she's a paleontologist at the Smithsonian Institute's National Museum of Natural History, says, quote unquote, the broad dense bones in gastralia acted as a diver's belt. So they have primarily evolved for the turtle, since they were from an aquatic environment, to actually fight against buoyancy and allow them to forage on the bottom of ancient lakes. We're not really sure why this would be favorable to them. It might be because it was a lesser inhabited niche, more available food source. We're not really sure. But we do know that they fed on soft-bodied organisms on the bottom of the lake floor, like modern-day worms. And so Ancient turtles at this time had long tails, which also attributes to why they were in an aquatic environment. This would aid in like swimming and things of that nature. We also know the ancient forms spent a lot of time out of the water. So they were primarily aquatic, and then when they started to come out of the water, they could only come out for short periods of time. So gradually they became to where they could spend more and more time out of the water, which have evolved into like our modern day like tortoises and things like that that primarily are terrestrial. And then a positive side effect of having a shell was protection against predation. And so in ancestral lakes, such as some that we'll talk about later, predators would ambush from underneath the animal. So we'll talk about more later, but in bone structure, the first thing to form is the plastron in the turtle shell, and that's the belly part of the shell. And so that would make sense that the predators are attacking from underneath, and that would be the first thing to be favored for, would be protection in the ventral area of the turtle.
Okay. Somebody's gonna have to. Okay, so fossil evidence is one of the most concrete forms of evidence we have of the evolution of turtles. So we're going to be talking a lot about that because that's one of the main sources of evidence we have. All right, so right here, these are cool little gifts we got for you guys so you can kind of visualize the transition. But first we're going to start off with, this actually starts from transitioning between Milleretta, which was a previous stage, but we're not really going to talk about because it was very lizard-like, between Milleretta and the Enotosaurus, which, as you can see, this is the Enotosaurus, kind of its final stage, which looks kind of like this. So you can see a lot of the vertebrae are starting to fall off at the end. I know some of y'all can't really see it because they're down here, but a lot of the vertebrae are coming off at the end. They're not really needed anymore because the vertebrae in front more are widening out, and the ribs are widening out a lot more. So you're losing a lot of muscle in there because the ribs are widening, there's no room for it. Also, you have movement of internal organs, so things are shifting around as the ribs are widening out on top. So that was kind of the first thing, the ribs started widening a little bit on top. You have a lot of vertebrae. Also want to point out that down here, there are the belly ribs, which I'm just going to call them belly ribs instead of gastrolia, because I think it's easier to visualize. Belly ribs were kind of overlapped like this with the back ribs, but then when these started losing a lot of vertebrae and this started widening out, they started coming a little bit apart, so the belly ribs were definitely on the belly, back ribs are definitely on the back. So, next. Alright, going to go on to the Papacellis, is right here, which is right here. Now, the picture's a little different because this isn't part of the video, but it was a very important part. The reason it wasn't part of this video was because this actually was only found about a year ago. So this was a very important transitional phase that they were looking for, and it kind of glued together the rest of the tree. So Papacellis, it's called the grandfather turtle because it's kind of really where the turtle structure started forming up. So the first thing and most important thing that happened in the Papacellis was the fact that it had the belly covering. That really started in here. Even though the ribs in the back did start widening a little bit more, it was mainly down in the belly area. So the belly ribs and the shoulder girdle started blending together to create that covering right here. And then also an interesting little point in the Papacellis was that it had the two holes in the back of the head, not in the back of the head, behind the eye sockets, that's making it a Diapsidia, or part of the Diapsidia group, which is why they're saying that it could come from lizards or crocodiles or somewhere in between, because back then it did have those two holes, but it's being slowly evolved that it doesn't have them anymore. So that's what. All right, next, this is the transition between Enotosaurus and the Odontocellis. Right here you can see. It does skip over this, but you can see it slowly start forming on the bottom. Those belly ribs are starting to widen out, make that nice covering, and this is actually where you get the 100% covering on the belly before you get the covering on the back, or the full covering on the back. So you're losing the singular belly ribs because of the widening. They're coming together, creating that one smooth slate. So for protection from predators and to get yourself on, or for the turtles to be on the bottom of the floor so they can eat whatever it is they ate, which was about soft organisms like worms and such. And then you have the loss of the sternum. Sternum, if you guys don't know, is this and us. Okay, so if there's a little turtle on its belly, then that means the sternum is going to blend into the belly ribs, creating that cover right there, which this one looks like this, Odontochelles. Next, you have the Odontochelles to the Prognochelles. These are all really weird sounding organisms, but so the Prognochelles. So this was a very important part. These are all very important, but this was especially important because the shoulder blades started moving inside the shell, which obviously the shell is not something you see traditionally, but then the fact that the shoulder blades moved to be inside of the shell was very important. So then you have the production of bone on the outside. I'm going to show you right here. As soon as you see the little dots that are showing up here, those were actually the shell starting to show up on the outside of the skin instead of just the plates inside of the skin. So right here you have that reptilian covering, reptilian layer of skin kind of covering those bones, even though you have the inside starting to make that shell structure. Right here you're seeing the shell is the outside structure. It's starting to be the first thing you see instead of skin. So it's moving like that. Finally, this one has a full covering on the back, even though it's not necessarily exactly what you would think of when you think of a shell. It does have the full covering, and so that's kind of an important little stepping stone. And then finally, Chelydra. Chelydra's right here, over here. That's definitely got a shell. You can definitely tell. It's got the full shell, which it's classified as a full shell, even though it has some holes on the sides, right here, and sometimes you can see it. But this, like right there, the holes in the side, but it does cover the entire body for the most part, which is why it's called a full shell in the papers. And then you have the shift of the collarbone, which we'll talk more about in a little bit, in addition to the shifting of the shoulder blades. The collarbone shifts inside of the shell, starts moving around a little bit. You start getting that really shelly structure, you know, nice round shelly kind of pot belly there, that kind of thing. And then we actually have a loss of a belly rib in this structure, which is kind of weird if you think about it, because at this point they already have that sheet of plastron, that plastron sheet in front of the belly structure. But because, all right, this is gonna be a little weird to explain, but so they had 4 pairs of belly ribs, like this. But as these started spreading out, you didn't need one of those pairs because the 3 could spread out anyways and cover the same amount of area. So there's no point in having that extra pair right there. So that kind of went away, and these covered up the rest of the area. So, all right, does that make sense to everybody? Awesome. And the video is not showing up, apparently, on this one, but
It was essentially just an animation which combined all of the GIFs and made the whole transition look
a little bit more
nice
clear.
and smooth. Yeah.
But it was just basically showing as these went through, and I would have explained it if it showed up as it went through these areas. So if it makes kind of sense to you guys, then we can just move on. So go ahead. You're gonna be up next.
Now we'll take a closer look at the development of the neck girdle and the turning in of the scalpulas. So we're going to begin with Milleretta. Like we said earlier, it was an ancient turtle relative, so not necessarily an ancestor, but pretty similar and helpful to understand when looking at the evolutionary transition. So as you can see here, it's pretty lizard-like. We have the scapulas represented in yellow, and the pink and blue bones, which are the girdle bones, and they're essentially your collarbones. And then the greenish blue is essentially your sternum. And as you can see, as the ventral plate and the shell develop, there's more of a need for support in the neck area. So a neck girdle forms, and the scapula splits, but it creates a Y shape, and takes form and replaces at one transitional period the collarbone. And this is why you see in modern turtles the scapula has basically formed a Y shape and is inside the shell.
And that's, you can see on the little turtle shell.
Yeah. So you see here, these are the scapulas. They come together. They form this plate inside the shell. So this is the belly plate. We took it off, and this is the inside. So these are the scapulas, which have formed this Y shape to support the shell and provide structure for the turtle.
So, phylogenetic Okay, so phylogenetic evidence, as you guys know, it's just kind of the tree of how they connect on the evolutionary scale. So we have down here Ankylosaurus, which is about here, which is right about here. So they were actually found, they lived about 260 million years ago, and they were found when we dug it up, present-day South Africa, which was pretty down there. It was kind of surprising to me to be that far away. Actually, it was very surprising that all these were so far away from each other. But this was about 260 million years ago, so they were way down here. Next, they found the Papacellis, which again was found last year, so it kind of brought all this together. That was found in present-day Germany, and that lived about 240 million years ago. Next, you have the Odinochelys, which was 220 million years ago in present-day China, found in present-day China. Then you have the Progonochelys, which was 214 million years ago in Germany and Thailand, which that was surprising to me that this could go to this in only about 6 million years, when these took about 20 million years each. That was very surprising. And then you have the you have that. Then you have the Chelydra, which was found in eastern United States. Now, I'm not going to say this is exact form is alive today, but the Chelydra is the same genus as the common snapping turtle, so that's pretty cool. She jumped a little bit. The common snapping turtle, which is alive today. So we kind of put it as alive today because it is kind of alive today in the snapping turtle. So another thing we have, excuse me, we have this, which is the numbers represent the percent of homology of the genes between a couple of these, which is basically the percent of similar genes, which show that they're related to each other. So then here you have 59% possibility, 80% possibility, and 64% possibility, and then the testudines. That's today's common turtles that are walking around today. So they're pretty likely that these were all related to each other. So based on times of when they were living, where they were found in the rock, and genetics.
All right, and so let's talk about some embryology evidence. Okay, so first off we have the turtle stages of development. And as you can see in the beginning stages of the development, you can't really tell the differences in the embryos of many tetrapods. I mean, there's not as big of a difference. But we do see as we go along, we have the cranium developing, the four-limb structure. However, as we get farther along in the development timeline, we see the development of the shell. And actually, it's harder to see in this one. We'll show you a more better suited image later. But there is no bony structure within inside of the turtle. The bony structure is all in the shell for the ventral and dorsal areas. So in these, really what I want you to take from it is how you can see the shell developing, and that'll be the distinguishing feature of the turtle. And then these are the stages of the lizard development. These are actual like drawings portraying the stages. But here we can also see, once again, the cranium developing, not very much of a difference from a turtle. However, what I wanted you to take away from this one is you can actually see, well, more specifically in the very late stages, but even in the mid stages, you can see the vertical column right here forming. In the turtle, we can't see that because it's being fused together in that top part of the carapace of the turtle shell. So what I wanted you to take away from this one was showing the vertebrae in the lizard stages. All right, and then so right here, this might help clarify a little bit more. These are actually stained embryos of today's turtles and lizards. So in the turtle embryo, the blue represents cartilage. It's not bone tissue. So the only bone tissue represented in the turtle, which is in red, is in the skull, and then we see it in the limbs and the digits of the turtles. But as you can see the vertical vertebrae column right here. And you can see the segmented parts of it, but it isn't a skeletal tissue. It is a cartilage tissue. Whereas here in the lizard, we can see the red indicating that that is skeletal tissue right there. It's a bone. It's very dense. It's a lot denser than cartilage is. And so if we go back to the turtle embryo, you can see right here on the edge of the ribs where it's dark blue, where the cartilage was, still is. However, here you can see the cartilage has formed solely to the soft tissue. And so the shell is gradually getting to where it's just one thing of the soft tissue instead of developing into the skeletal tissue with cartilage in between to allow for flexibility. This is a lot more rigid. And also in the lizard, you can see a lot more of the skeletal tissue, especially even in the digits, you can see a lot more red present. And then also down here, we have the comparison of the lizard embryo, the turtle embryo, and a bird embryo. We used a chicken. And so this will link back with our 3 hypotheses. As you can see here, this is in the late stages of development. But in the bird embryo, we have a beak has formed. There's differences in the arms and legs of the bird embryo. And in the arms, it's going to form a more webbed structure, obviously because it has wings. And it has a somewhat of a tail. It's not as distinguished as a lizard or a turtle tail. And if this was in more of an HD quality, we would also see the pores on the bird embryo where the feathers will eventually be. And then there's a lot more similarity in the turtle and lizard embryo as we suggested in our earlier hypotheses. The only real difference is, once again, the shell, but they do have the distinguishable tail. All 4 limbs are of similar structure. We don't have a web structure and then a digital structure. Cranium, eyes developing. It's showing the far more similarities in between the lizard and turtle clade instead of the bird crocodilian clade to turtle.
All right. Finally, we'll look at the variation in extant turtle species, and due to lack of fossil evidence and other forms of evidence, we don't understand how this variation formed very well. But essentially, all turtles share the common features of the shell, the scapulus being inside the shell, and a common skull. And they're all organized into the order Testidia, and which is broken down into 2 suborders, Cryptodira and Pluodira, which are based off how they move their necks. So most turtles, so tortoises and snapping turtles, all when they get frightened or stressed, they move their head inward and they retract their neck. Whereas several other species, like this snake neck turtle, they can't do that because their neck is so long. So what they do is they actually turn their neck inward, and they're called side neck turtles. The turtles, there's 14 families, and these are 8 of the most significant and most diverse groups. So first we have sea turtles, like this green turtle right here, which is primarily saltwater based. Then we have tortoises, snapping turtles, soft-shell turtles, pond turtles, which is what we used in our example earlier, the skeleton of a pond turtle, side neck turtles. These are Asian river turtles, which have a very distinct ridge on the back of their shell, and leatherback sea turtles. 2 of the most ancient groups are Calidra, so snapping turtles, and leatherback turtles, which have changed very little over the past 100 million years. If you look at soft-shell turtles and leatherback turtles, you notice that they don't have the segmented or square plates like all other turtles do. These plates are called scutes, which are made of keratin, and they're essentially just little scales that can either build up like they do in many tortoises to form either conical structures, or they just fall off and appear flat like they do in most turtles, especially sea turtles. Also in soft-shell turtles and leatherback turtles, the ribs are more splayed. They aren't as widened. So instead of being connected by the ribs being fused and connected by bone, there's instead just cartilage in between these ribs.
Really quick before we finish, there you go. I do want to show the video that we were trying to bring up earlier with the structure of this, because I know it was really hard to understand for us even with the pictures. So you're gonna.
Yeah. So this will tie together the development of the neck girdle as we discussed earlier.
So you see this is moving in back, what I was talking about earlier with the
Yep.
back, and then you can go from there.
Yeah. So here's the neck girdle forming. The collarbone is moving up to create more support, and as you see here, the scapulae are widening and also creating more support. The collarbones go down, and the scapulae move into place, and here we end with essentially just a modern day snapping turtle. All right. Let's open our studio audience floor to any questions.
Question?
Can you guys talk a little bit to like sea-dwelling turtles versus land-dwelling and like the differences that we see between those?
So there's really not too much difference besides diet, but if you like look at the anatomy and bone structure, the paddles are essentially just kind of similar to bats. The fingers have just kind of widened out, and skin and plates have like formed over top, just forming paddles. Yeah.
Nice.
Any other questions?
So what do you guys think after everything you saw? What is, out of the three hypotheses, what do you think is the most valid?
I would go with the lizard clade.
Probably lizard clay, to be quite honest.
What do you find most convincing about that?
Embryology to me seemed very similar. Whoa. Also, if you like look back at the earlier ancestors, so Milleretta and and the one after that. Anyway, they were much more lizard-like, and they're like the same size, and also they didn't really show as many crocodilian-like features.
The only thing that really threw it off would be like the phylogeny of it, because that seemed to agree more with the crocodilian clade. But that was really the only thing that we found that went against our main hypotheses that we consider to be the truth.
And what was the basis of that phylogeny? Was that like a molecular phylogeny or a trait-based phylogeny?
This one was a molecular phylogeny that because that was the one of the hypotheses that we considered. So it was the molecular base.
So what kind of predators were crunching on these early forms that just had a belly? Do we have any idea?
I would think anything with a strong enough jaw to break through the bone. So, well, the turtles were actually not very big back in the day when they were the size of, the first lizard form that we had was only about the size of this long. And that wasn't a turtle, but it was, lizard kind of turtle-y-ish, that kind of thing. So, anything kind of big enough that could crunch through the bone, pretty much it's fair game. Until it got that real turtle shell, that real shell structure, the spines on the one of them. You guys remember the spines that were all over the one of them? That was going to make it a lot more difficult for something to crunch down on it in the jaw, because that would hurt. I mean, you guys ever biting into like a chicken bone, it hurts. So I would think just anything that had a strong enough jaw to break through it.
Also, I would say most likely ambush predators, because instead of evolving to like run away, like if they were being chased, they just developed like a hard boning plate. So if something like grabbed them really fast, it would be like more difficult to like eat them.
Well, around here or down along the coast, it's going to be gators. And crocodilians are a whole group too, so they've probably been co-evolving together for a long, long time.